Okay, let's get started with the second session. The first speaker for this session is Navin Chaurasiya from IUCA, and he'll tell us about the galaxy halo connection using HSC photometric galaxy.
Can you hear me? Yeah, okay. So, yeah, I'm happy to be at ICTS and thanks for inviting me. So today, so my name is Navin Chaurasiya. I'm a PhD student at IUCA and I work with Professor Surudmare. And today I'll be talking about my project on galaxy halo connection. So, yeah, so let's see. So the question, right. So the question that we ask is, so first of all, I would like learning. So we have been talking about modeling the understanding the particle nature of the dark matter halos or different things, dark energy, and understanding or modifying cosmology to get consistent explanations for many probes and so on. But among all these tensions, there is one more element of understanding the astrophysics of galaxies and their connection with dark matter halos, which is a piece in the puzzle also. And so my talk is in respect of that. So the thing is, we know that the halos are dark matter halos are biased with respect to the matter distribution, and the galaxies reside inside the dark matter halos. So that is the reason why we use galaxies as traces of dark matter halos. So the one question is, how do galaxies populate these dark matter halos as a function of redshift and as a function of the properties of the galaxies itself? So this question, once we understand, we'll be able to better understand the it will be a help in understanding the how the galaxy properties and halo properties they evolve, and what kind of scatter is there in the astrophysics of this relation. So so like one of the results this is a key result that I am interested in. So the stellar mass halo mass relation, this is a plot from Banerjee et al. 2010, and there are more recent results also, but difference is not too much. So I'm just going with this one. So you will see that as you go on the vertical axis, stellar mass increases, but you also have to look at the slope of this curve. So slope is a little bit higher compared to the high mass end. So you say that, okay, specific star formation rate is higher, and on the other axis, you will see that the halos, dark matter halos are accreting more and more dark matter and becoming heavier. So that is the other axis. And the ratio is kind of the efficiency of star formation kind of thing. And this encodes the understanding how at what mass galaxies are more efficient in building up baryonic mass, and how are their dark matter halos growing at the same time. So so this is the question that I'm interested in, and so these are the abundance matching constraints, and we will be using weak lensing as a direct probe of masses, because in abundance matching and you infer the relation, there are assumptions involved. One of the key features of key aspect of lensing is that you measure the dark matter total matter directly, right? So so I'll just quickly try to go with the basics of the lensing for if there are students who don't work in this field. So you have to look at this between the planes here. So this is the observer here. There is some background thing. So let's think that this is some galaxies distributed at some redshift. So these are we call them as lenses. So there will be some background galaxies behind them. So the thing is, if you just look at them, this is the observed plane, right? So I'm just showing you what happens if there is no weak lensing. So what will happen is these yellow things are the galaxies, lens galaxies, and they are also randomly distributed according to each other. If there is some and the white galaxies are like these background galaxies, and these background galaxies, their shapes are also randomly oriented with respect to these lenses. But in observed plane, what happens is you don't see that kind of thing. What you will see is the shapes of the background galaxies will have some tangential component induced because of the lensing. So you will see that these white things will have slightly tangentially oriented. This is an exaggerated picture, but just to give an idea. Now, the weak lensing signal that we measure here as a function of radius, it has like two components broadly. One is the shear, tangential shear, average tangential shear, because we will be stacking over a lot of lens source pairs. So this average is for that. And there is another component, which is the geometry, which relates the geometry of the distances between observer, lens, and source. Okay. So Okay. So what kind of data we use and how do we measure it, right? So that is one thing that I want to quickly tell you. So in HSC, we use this wide layer galaxies where the number of galaxies are pretty high. I'll be talking about these two redshift bins, Z1 and Z2. So Z1 is like 0.3 to 0.55, Z2 is 0.5 to 0.80. These galaxies, so we'll be binning these galaxies as a function of stellar mass thresholds. You will see on the x-axis is the stellar mass. So all the galaxies greater than 8.6, those numbers are like 10 to the power 6, something like that. And so on. So this is the number distribution, just for quick understanding. So we'll be using some 6 fields in the HSC. And the photometry that we'll be using is photometric data. So the stellar masses and redshifts are derived from a Mizuki catalog that we'll be using here. And the total area that we'll be concerned with is 126 square degree roughly. And also because our lenses and sources fall in the same data, so there will be full overlap. Why this full overlap is important, I'll tell you shortly. So these are my binning schemes, stellar mass thresholds and redshifts. Okay, so how do we measure these signals? So first, so what we have to do is you have to realize that this is measured at different radii. What is this radii? It's a projected radial distance. So what you need to do is you need to count the pairs of lens galaxies and source galaxies in the background. Lenses are foreground, source galaxies are background. So you count at a given separation how many pairs are there, right? So more the pair, better the statistics, and better will be your signal to noise ratio. So the key thing in weak lensing analysis is that if you have more and more area, that's why then you will have more and more lens and more and more lenses. And if the overlap is better with the background galaxies, you will have more and more sources. So the lens source pair will increase in count, and the errors will go roughly as square root of n. So more the number, and you will get better signal to noise ratio. So, and secondly, the geometric factor has this form roughly, exactly actually. So it has distance to source, lens, and between them. And I just want to point out the feature of this this function is that when the lens and source are very close by, this function peaks very sharply. Otherwise, it falls off very quickly. So that is one feature. I will. So this is useful when we average it. Okay, so I'll just let me just go. So I'll tell you. Okay, so yeah. Okay. So while averaging, we also weight it by some weights based on the lens source quality, based on the quality of the shear that you have measured, quality of the tangential shear that you have measured, and various aspects. So this sigma crit is used as a weight, and I will show you what combination we use there. Which is sensible. So there are issues in how you separate sources from lenses. So there are some things that we use to tackle this thing. So one is separation of sources versus lenses population with if we use full PDF, because we don't have the spectroscopic redshift, so we use only the photometric redshift, right? But we have a PDF of this redshift. So what we say is that if there is some redshift, maximum redshift of your lens, then ZDiff is like 0.1 for us. So you say that if the overlap of the source redshift PDF is greater than 99%, plus some factor here, only then you take it as a source. Otherwise, you just skip it, because there is a high chance that it could be a lens, a galaxy related to the lens distribution. So these kind of contaminants, if you don't remove, they contribute to your lensing signal and they dilute the lensing signal, and then your interpretations will be off. Okay, and see, the other thing is using full ZPDF while stacking the excess surface density. ESD signal is basically excess surface density signal, which is nothing but the lensing signal, to avoid contamination again. So yeah, so this sigma crit inverse, like I told you, sigma crit peaks very sharply when the lens source are very close by. So inverse of it is it will be very low when the lens source galaxies are very close by, and far off when they are far off, it will be high. So this weight kind of gives more weightage to galaxies which are separated, lens source pair which is separated largely. Otherwise, it downweights other things. This also helps in kind of curbing the contamination. Okay, so this is the full equation that we use for lensing measurement, and there are many data related things, factors, some multiplicative bias, some additive bias. But overall, the understanding is the same. This ET is the tangential component of electricity that you measure, how much tangential shear has happened. And then this is the kind of weighting thing. This WLS is the weight for this stacking, averaging. And this weight is a minimum bias estimator kind of thing, right? So now once you know what is the weak lensing signal, how you measure it, I have not talked about the factors, multiplicative and additive biases because of lack of time. So I'll just go ahead. So signal measurement in, okay. So let me just skip it. So these are all just related to systematics, and we have checked that the systematics are within bounds. Okay. So I'll just try to show you what are my results. So once you measure the signal, then you also have to model it to infer some halo masses and other properties of your galaxy distribution. So in the modeling, there are central and satellite functions that halo occupation distribution functions, which are used to fill up the halos of certain mass with galaxies. So I'll also skip, I'll just mention that there are 5 parameters. This log m min is the mass of the central halo, and this is the scatter in the central halo. And I'm more interested in these 2 parameters than the satellite parameters, so I'll go ahead with it. And so there are some priors in this modeling. So we use a Bayesian analysis, and where the priors are mostly the flat and wide priors, just to keep it uninformative. Right, and these are just the constituents of my modeling, so I'll skip it too. I just want to show you the results. So these are the fittings. Now the key feature is that the signal to noise ratio in observation is like 50 and above, which is very nice. So this gives us good constraints on the fitting. Now clearly the modeling succeeds in fitting the signal, and yeah, and this blue, I just want to show you the blue signal. Blue signal is a result from HOD modeling of abundance and clustering using the same data that we have used. And clustering data doesn't reproduce a lensing signal. So what we are doing, we are using abundance and weak lensing to fit the signal, and then see what are the stellar mass halo mass relations compared to the clustering analysis. Okay, so this is in another redshift bin, and again the fitting is very good, just that the signal to noise ratio is a little bit lower because number statistics goes a little bit down. So how are the constraints looking? So the stellar mass halo mass relation that I talked about, this is a parameter in the modeling. Okay, just to heads up, this min parameter is not the best constraint by the weak lensing. Best constraint parameter is the average halo mass, which I'll show you next. But this is a relation which has been compared in literature, so I'm showing you. So this is the 1 sigma and 2 sigma error bands in my analysis, and the clustering analysis is here, this red point with error bars, Ishikawa. What you will see is at the lower mass end, they are kind of consistent at slightly at the lower halo mass end, but at the high stellar mass end, lensing predicts little bit higher mass. However, as I go to higher redshift bins, they become more and more consistent. This could be the reason could be that at high mass, at high redshifts, here the HSC's median redshift is close to this redshift. So that means HSC will have better photometry and better modeling of galaxies. So probably redshift and stellar masses will be better here. So there are components to understanding this plot. Okay, there will be errors in the stellar mass. So a stellar mass is for us is just a label. It just tells me from a catalog I have a stellar mass, and halo masses are my inferred values. So this understanding, this is also a task which we are currently doing right now. Yeah, it's not changing, huh? Right. Just, yeah. So I'll just quickly tell you that once you use abundance, so the errors in abundance have consequences on your understanding. So if I just so you see that this orange one is little bit higher abundance than the blue one. Blue abundance is coming from the clustering analysis that I'm comparing with. So those are here. So because lower abundances will use slightly higher halo masses here. If I take higher higher abundances, this will go down a little bit, but it also have its consequences on the sigma log m, right? So keeping that in mind, so if I were to believe that what are the constraints on stellar mass halo mass relation, using the abundance from I20, that is the one clustering analysis, and this is some Muzin et al. 2013 analysis. So what you will see is that the trends in the stellar mass halo mass relation here, if Z1 is at high mass end, if Z1 is giving you higher halo masses, then that has potential to change with the information of abundance. Similarly, the abundance is also controlling also your this sigma log m. So this inference has to be kept in mind. But at the same time, the best constraint thing here is the stellar mass halo mass relation. The average halo mass relation as a function of the stellar mass. So what you will see, the error bars are much smaller, and this is kind of trend. I would just mention it in the results section in my conclusions. And just this is the last plot which shows you what happens if I only use weak lensing and if I don't use abundances compared to if I use abundances. So these hatched regions are with the weak lensing only. So it clearly shows you that the fitting is not completely dominant, or it is not dominated by abundance. It is weak lensing is setting the bar for the halo masses, and abundance, inclusion of abundance kind of brings it a little bit down. So this is just one abundance from the clustering analysis. If I include other abundance, so you will have slightly here and there. So I'm not including that plot here because of to maintain clarity. Satellite fractions, there are features. It's just that satellite fractions go down as you go to higher central mass, stellar masses. It is hard to comment on satellite fractions trends by using either only abundance, or by either using only weak lensing or both of them. So I won't comment on this right now. So these are some of the results, and yeah, if there are some questions, I'll show you some other plots. Thank you.
Okay, time for one small question while the next speaker sets up. Anyone question?
So why do you, I don't think I quite follow why the differences between the previously measured min as a function of halo mass is worse at higher masses. Do you understand why?
Right, you mean?
At like higher halo masses.
At higher halo masses?
Higher stellar masses.
Mm-hmm. Why this? So this is redshift bin 1 and redshift bin 2.
Yeah.
What you are asking is why they evolve in redshift.
Yeah, particularly at higher stellar masses.
I'm trying to compile all these understandings. I don't have a very clear idea of it. So yeah, let me think for a second, or maybe I will.
So we can chat.
Yeah.
Later also. Yeah, because you said that it might be because the HSC redshifts are better higher at higher redshift. That's the median redshift of the HSC survey.
Well, when I said that I said that as a possibility because why previous studies are matching better. I'm not biased to previous studies, but I'm just saying that could be a possibility, because it is true that photometry becomes better at median redshift of the HSC. That is true. And there are error bars on the x-axis. So this has potential to shift on the x-axis also. So that is also a critical point actually. So this understanding is, I'm trying to understand by using simulations and try to see if I take true if I take true stellar masses in simulations and if I give it some scatter, what happens? What I have clearly seen is that including scatter in, let's say this is the true, these are the true stellar masses. Okay, let me clearly tell it. If I take all the some galaxies in some redshift bin and in some threshold stellar mass, okay, and then I perturb the redshift of these galaxies by some scatter, realistic scatter. I got that by comparing with Cosmos data. And then what I do is, then I can also perturb the stellar masses of these galaxies just because the mass to light ratio will shift if I move it up and down in the redshift. So what happens then? I bin those galaxies in observed redshifts and observed stellar masses. So this is, let's say if this is my stellar mass limit, like 8.8 or something, maybe 8.6, then in true plane, if you see, what you will find is it is slightly heavier. It's not really the lower threshold. So that means all those plots that I showed you, it could potentially shift on the x-axis towards maybe agreement with the previous studies, but still it will have a large error bar. So the point of this study is that you can do such kind of analysis by using photometry, better photometric data. As future surveys will come, this thing can improve. And not only that, there is some more potential in it. If I combine some other probes, if I combine some other probe like clustering or something, then this can improve. Also, if I take joint fitting, then again it can improve because of the covariances across planes. So modeling of covariances can become better.
Okay, let's thank the speaker again. And now we have Shambho next from IIT Kharagpur.
Okay, good afternoon. I would like to start by thanking the organizers for giving me this opportunity to present our work here. So the title of my talk is Bound on Self-Interacting Dark Matter from Galactic course. Okay, so to start with, like many, I'm also a believer that dark matter to be of particle in nature. And so therefore, the best way to ascertain its particle properties and its phenomenological studies is to probe its interactions with each other. So in this case, one of the best things to do is, one is to look into the interactions of dark matter with the standard model sector. And in this case, one can look into the effects of direct detections like in nuclear recoil experiments or sub-GeV dark matter scattering, or even in indirect searches like dark matter capture inside celestial objects, and also in collider physics where one can look into missing energies. Alternately, one can look into the scattering of dark matter within the dark sector itself, which is the self-interactions, and which is the title of this presentation. Okay, to start with, so what self-interaction does, it basically opens up a channel in which dark matter can now communicate with each other, and therefore, so there is an exchange of energy and momenta from the warmer peripheral regions to the cooler inner regions. So this kind of helps in thermalizing the central region of the galactic halos, and the extent of these thermalized regions is basically a function of the strength at which dark matter can interact with itself. And also, as very much evident from here, is that this kind of reduces the central density of dark matter at the central regions. Okay, so this is a very simplistic algorithm of the simulations that we have followed. So what we have done is we have simulated around many dark matter halos in the mass range of 10 to the power 10 to 10 to the power 15 solar mass, and we have considered a self-interaction cross section of between 0 to 10 centimeters square per gram, where 0 is the collision-less dark matter scenario, and we have done this for around 10 to the power 6 number of dark matter only particles. And for getting a better idea about the statistics, we have performed each simulation for a particular mass and cross section around 4 times to get a more better understanding of the statistics. So once we have our simulations ready, the results are ready, what we do is we extract the core radius from our simulations, and as evident, this is a function of the halo mass and the strength of self-interaction. Also, alternately, we have looked into certain galaxies where we have looked into their observation data, and we have similarly extrapolated the core radius as a function of mass. So with these two parameters ready, we are now in a position to compare them and provide some bound on this specific self-interaction cross section. Okay, so this is a result in product of our simulation. So on the left panel, we have plotted the velocity dispersion as a function of the radial extent from the center. So as you can see that a collisionless scenario is quite less thermalized, whereas once we introduce self-interaction, we see the core to get heated up, and the effect of thermalization basically sets in. This same effect can be realized if we look into the density distribution of dark matter, where we see that as we keep on increasing the self-interaction cross-section, we see the number density to kind of go down, and the extent of the core radius also increases. So this is kind of what we expect from our understanding of self-interaction. Okay, so here just to give a brief idea about the statistical stability of the analysis. So on the left panel, we have plotted this delta RMS basically quantifies the goodness of fit of our simulations with the with our modeling. So as we see that as we move on to larger cross sections and larger mass halos, so we see that the fitting kind of falls a bit loose there. That is most likely due to the limit of our resolution. And on the right panel, I am showing we have performed a convergence test where we have looked into different number of particles, and we see that taking around 10 to the power 6, 7 number of particles is kind of okay, because there is not much significant change in the density distribution, particularly at the central region. Okay, so this is the legacy data that we have used to compare our simulation. So we have used data from dwarf spheroidal, low surface brightness galaxies and galaxy clusters. So what we do is we start with the observed rotation curve and we convert them to density profiles using this simple-minded formula. So, and here I am showing the fits that we obtain for our simulation and the simulation for two different density profiles. One is the code NFW distribution, which is given in the red, and the green is the genes or the semi-analytic distribution. By the way, one can look into other distribution profiles as well, which we have, but we find that the errors in fitting is comparatively less for these two, so we have stuck with them. Okay, and here I've shown for different cross sections and the different masses for the density distribution and their corresponding fits, where the vertical lines is the estimated core radius for our simulated halos. Okay, so now since we have both the ingredients ready, so one from the observed data and the other from simulations, we are now in a position to compare them. So on the y-axis, I have the core radius as a function of the dark matter halo mass. And the left panel is for the semi-analytic distribution and the right is for the code NFW distribution. So here the three colored curves, orange, red, and brown, are for three different values of scattering cross section, whereas the magenta line is for the observed data. So, and the vertical lines are the error bars corresponding from simulation and the fittings related to, and the errors due to fitting. Okay, so finally, when we have both the core radius estimates ready, what we do is we perform a chi-square test, and where we try to constrain the dark matter self-interaction cross-section. So on the y-axis, I have the reduced chi-square, and on the x-axis, it is the specific self-interaction cross-section. The green and yellow panels are for the 1 sigma and 2 sigma confidence, and the vertical lines are the existing bounds from all which are already available in literature. So as one can see that for the wide range of halo mass that we have considered here, the semi-analytic distribution prefers a zero scattering cross section, which is the CDM scenario, whereas the code NFW profile prefers a small but non-zero scattering cross section. Okay, so finally to summarize, so dark matter self-interaction leads to thermalization and helps in core formation, and the strength of which is kind of governs the extent of these thermalized regions. And comparing the distribution of core radius as a function of the dark matter halo mass from simulation and astrophysical observations can provide a useful handle to explore dark matter self-interactions. So for our case, a very simplistic velocity independent point-like isotropic interaction, we provide a conservative bound of around 9.8 centimeters square per gram at 2 sigma confidence. However, the bounds that we present are very much sensitive to the distribution of dark matter that one takes into account, particularly at the central region, and obviously they are very much sensitive to the resolution of the simulation. Thank you, and this is based on this work which has been done in collaboration with Tirtha Shankar Ray and Abhinash Kumar Shaw. Any questions?
Questions?
Nice talk, thanks. So you simulated these halos? How did you initialize them? Are they isolated halos? And if so,
Yes,
how are they initialized?
they're isolated halos.
So how do you initialize them? What are the initial conditions?
So what we start with, we have started with a cusp-like initial condition, and we have seen them to thermalize once we evolve them with self-interaction.
And if you initialize a simulation like that without self-interactions as just a cold end body simulation, does it go to like some expected NFW like profile?
Yes, yes.
It's consistent
yes.
in the zero cross-section limit.
Yes.
Thanks.
Yeah. My question is regarding that velocity dispersion as a function of radius and the density. So does that profile depends on whether the self-interaction is kind of attractive or repulsive?
No, so this is just like a point-like interaction. Okay, so if you look into, I mean, it's like a hard sphere scattering. So are you talking about the velocity dependence?
I'm asking, does this depend on the kind of interaction that the dark matter particles are having, like attractive or repulsive? I mean, effectively.
Oh, okay, yes.
Yeah,
Okay.
yeah.
You can approximate like that, but however, I mean, the nature will be same if you consider any other kind of profile. It won't be very different because this is like just a change. I mean, this plot just tells you that when you introduce interactions, what happens. So whatever model you take, this simple feature will exist.
Because the way I will think is like if okay.
Any other?
How do you define the core radius for these analysis?
Okay, so like I've showed some profiles over here. Okay, so if you look into the semantic profile, so you see that within this radius R1, it follows like an isothermal distribution. However, outside it again goes down your regular NFW. So this R1 is kind of acts as an estimate of core radius for this profile. However, if you look into other profiles like we have done here, so this has an innate core parameter. You can also find other distributions which similarly have an innate radius distribution.
One last question.
Hello. Yeah, so I was wondering, does this core cusp problem that SIDM tends to solve, does it depend? It depends on the cross section, no?
Yes, cross section is an important parameter.
Yeah. So if you have like very large cross section, around 10 or something, so how would that affect the problem, like the core cusp problem? And
so the issue is to solve the core cusp problem, but again, you have like different class of galaxies. You look at like you have different relative velocities. Like for Milky Way, you can have around 200, or dwarfs around 10 to 20, or clusters maybe around 1,000. So in that case, you won't have like a single scatter might not be good for everything, single strength.
But sigma V has to be same, no?
Sigma V.
Yeah, I mean the cross section.
Sigma over M, right?
Yeah, sigma over M. And that has to be one fixed value, or it can be variable?
Yeah, it can be variable. Like here we have tried to do it like we have considered one value that tries to solve for everything, but that is very, again, a conservative bound, because a more idealistic way would be to have different at different velocities.
Right. Okay, thank you.
Okay, let's thank our speaker again.
I'm Harsha Saxena. I'm an undergraduate at IIT Bombay, and today I'll be talking about, forget the mouthful, basically just the impact of modified gravity theories on structure formation in a context of kinetic field theory. So before I start, I would like to thank the organizers of the conference for allowing me to speak at this conference. It's a great honor. Secondly, I would like to thank Professor Matthias Bartelmann, who firstly facilitated this entire project, and his entire group, Alex, Johannes, Ricardo and everybody else at Heidelberg and beyond. So firstly, firstly, I'll start out with the motivation of why we really care about this. There are a lot of deep and dark questions that have been plaguing humanity for a while, especially in the context of structure formation, which have been, how do nonlinear structures form and evolve? And is there a first principles approach to study structure formation? Now, for those of you who attended the cosmological perturbation theory lectures, we know that you can model dark matter densities of fluid, and we have a pretty good idea of the linear structure formation. But once things start to go out of hand when we move into the nonlinear regime with the whole density perturbations and what is called the shell crossing problem. So the way people solve it is basically using n-body simulations. So this was a starting point where Matthias and his group started to think about what if we do a statistical version of the same, which brought us to the point of kinetic field theory. So that kinetic field theory is basically a statistical field theory for classical particle ensembles, which basically means now that you live in phase space. So you don't have this problem of shell crossing anymore. So it's basically a Hamiltonian problem. So you just have an initial condition, you use Hamiltonian dynamics to sort of evolve the trajectories. The main thing which has the information of everything in kinetic field theory and the information of your entire system is what is called the generating function in Z, which you can just basically think of as a generalization of your partition function from thermodynamics. And it looks for general cases something, looks something like this, the Z over there, and where PQP is sort of like the initial probability density. If you solve this, you will basically, through Hamiltonian dynamics, and J is sort of the generator fields, you will get that the equation of motion is basically some inertial motion plus the interactions, which is basically what we want to model. So kinetic field theory is something which is completely general. I remember attending a talk where some biologists used KFT to study structure formation in cancerous cells, but I think we should stick to cosmology here. So we can write out our equivalent Hamiltonian as the first line, which is basically a mass dependent as a function of the mass, which is time dependent in our case because co-moving coordinates. And we have the Poisson equation. We can also choose the main point that we'll be doing is choosing our time as the growth factor, because we want to see linear growth and then we want to see deviations from that linear growth. So once you work out the entire math of KFT, I'm just putting the results there because KFT is too huge for me to cover in the tiny time. You get that the Q of T is basically the linear Zeldovich trajectories, and the deviations from those Zeldovich trajectories are basically governed by this function phi, which basically which is sourced by the nonlinear density fluctuations, which is pretty convenient once you think about it. You have Zeldovich trajectories, and the deviation from those trajectories are sourced by what you want, which is the nonlinear density fluctuations. You can go a little bit further. You can define what is called a density operator, which is basically the Fourier transform of the individual delta functions. And from there, you can get the 2-point power spectrum or density, which is basically this, evaluated at the generator field 0. From here, you can also get the 3-point cumulative, 3-point functions and the bispectrum and so on and so forth. But we'll be focusing on this over here. One thing which, so now that we finally want to encode interactions is using what is called the interaction. You can define interaction operators and do the same thing. I'll not go into that. But the final result from all the math of KFT is that the nonlinear power spectrum depends on the linear power spectrum with the interaction operator, which looks something like this. So forget about all this. The interaction operator basically encodes, is a function of the convolution of the one particle forces, so the one particle potential, which is V, and the sort of density over the initial, the linear powered spectrum of the particle. So it's how do you affect each other is basically, the interactions between particles is basically the forces between them, along with how they are distributed in space, which makes sense. So just to build in the fact that this is related to reality, we are grounded in reality in some way. You can see that this is the linearly evolved power spectrum, and the KFT power spectrum is actually pretty close to what we expect from numerical simulations of spherical collapse models. You can see over here that agrees pretty well up to 10 H megaparsec inverse, after which the mean field approximation starts to fail. So on to the main topic of the talk, which is on modified gravity. So there has been a lot of work done in the last couple of years on encoding dark energy as a sort of large-scale modification of gravity. But one thing that we need to make sure is that you need to have screening mechanisms, because you know GR works well on tiny scales, say solar system and so on, because GPS works, we don't fly off hills. So you need to make sure there's some mechanism to turn from this large scale modification to this to GR, and that is what screening mechanisms encode. And there have been a lot of work on this, but we'll be working with Hassani et al. And Raiser's work on the modified Poisson equations can be in this modified theory of gravity with this effective scale dependent gravitational constant, which they get from simulations. So these are dependent on a bunch of parameters. A is basically 1 if you want to tend to GR again. Capital B, small a, small b are functions of the model. So depending on what model you use, depending on what the screening mechanism you want, you can change the functions of these are the number of screening mechanisms, and these are basically the function of the model. K star is sort of something that parameterizes your screening wave number. So it's basically where you change from modified gravity to say GR. And this is the kind of simulation that we got. So the boxes are basically where the linear the solutions of the numerical codes and of the spherical collapse models, and this is using this sort of parameterization. So that works pretty well. So what we will be doing is, as a first approximation, we'll be fixing our growth factor as the lambda CDM one, and the only effect of this modified gravity will come between interactions. So the interaction operator, which was a convolution of the one particle force, which is basically a Yukawa kind of force, along with the power spectrum. So once you do a convolution and you have a scale dependent effective gravitational constant, your interaction operator would look something like this. And we've plotted it for NDGP models, which is a special kind of modified gravity model where apparently our our 4-dimensional world is embedded in some 5-brane world model, and you have some crossing parameters and stuff. But this is how the power spectrum, the relative power spectrum looks like. And you can see the strength of the variation and sort of where it turns over depends on our screening wave number, as it should. The screening wave number. So yeah, K star, which also encodes at what scale you start to change. This is with KFT. This is with KFT. Yeah. So finally, another thing that we've been working on for a while is using Taylor approximations to make our life easier. So what we would expect, because lambda CDM is pretty nice, we would expect tiny perturbations around GR. So you would express our nonlinear power spectrum as a functional first order Taylor approximation around GR. So if you have a change in effective constant G, as you do in the models that I just talked about, you can do it sort of as a first order Taylor approximation. Why is this useful? Is because this functional derivative of the power spectrum, of the nonlinear power spectrum with respect to G, can be evaluated at GR. So that's it. You just need to do this once with the models that you already know with GR, right? So basically, if you give me a delta G of any modified gravity model you can dream up, you can interpolate it. I don't care. As long as I have a delta G, you can give it to me, and I can basically spit out the nonlinear power spectrum that we expect from simulations. Just to give you an idea of how this power spectrum looks like, if you plot the change in the interaction operator at some fixed K and say today, with respect to the change in the gravitational constant, so basically you're introducing a change in the, you're modifying the gravitational constant at some perturbance wave number alpha and some perturbance scale factor X. So the change in the interaction operator is dependent on this, and you can see that if I want to evaluate the change at K equal to 1, I should introduce the change in the gravitational constant at K equal to 1, which makes sense. And also, if I introduce it very early, if I introduce delta G just very early in the beginning and leave it there, and since it's linearly evolving, the power spectrum won't change that much. But if I introduce it later hand, it will sort of increase. But again, if I introduce it very close to today, it won't have that much time to settle in and change the interaction actually. This is a similar thing, and I don't have time to talk about it. It's the exact same thing basically. So just to tell you that the Taylor approximation is indeed good enough. We've cheated here a little bit because we have taken only tiny, we have fixed our parameters of K star so that we only have tiny deviations from GR. So you can see that the exact thing from what I did before, which is this, versus the Taylor approximation, which we talked about right now. they actually agree pretty well for all these models, which is NDGP with Weinstein screening, camouflage screening, Yokawa screening, and chameleon screening. And this is the sort of the functional derivative in full gory glory. And another thing which I just wanted to mention is something that we're currently working on. Yeah, which is something that we're currently working on, which is that if you remember, we just introduced our changes only in the interaction term. So we fixed the lambda CDM. But of course, if you have modified gravity models, you would also change your linear growth. And if you want to evaluate it only in the because if you do it the full thing in KFT, it becomes complicated. So you want to do it only as a Taylor expansion. So you will also have this additional derivative of the growth factor with respect to the G. And you would have to include that in your power spectrum, because your power spectrum, of course, depends on the growth factor. And you can solve that using this thing which Alex and a bunch of others have already done. Another thing, if you want to start comparing with observations, is because now that your growth factor has been affected by the modified gravity model, your amplitude of the linear power spectrum would also change, because that's just d plus squared into the initial power spectrum. And once that changes, you already know from observations what the linear power spectrum looks like. So you can sort of change it by this amplitude so that it starts off beginning differently and it eventually grows to the same thing that we observe today. So using this, we can sort of try to compare with observations and derive constraints on the parameters of these modified gravity models with the expected spectra and the observed spectra, but that's relatively in the future. So just to summarize, KFT is an analytical particle-based approach for nonlinear structure formation using generating functionals and mean field approximations. You can have a large-scale modification of gravity, which will give you, with screening mechanisms, which will give you an effective gravitational constant, which depends on scale. And you can compute the power spectrum of these as predicted by KFT. And we know that KFT agrees pretty well with simulations and is very, very comparatively much faster. And you can also use a first-order Taylor expansion if things get too hard to compute deviations from GR in a wide class of modified gravity theory. So yeah, thank you.
Actually, I'm just trying to connect this formalism to say the effective field theory of large-scale structures. So can you go back to slide 7? Are you assuming that that interaction term you're writing down is the lowest order one? Is that why that's d plus square?
Yes. So if you do the whole thing, it comes like 1 plus iota SI plus so on and so forth. So it's
I think I see the thing.
Yeah, yeah.
Maybe I missed this, but so the KFT is very interesting formalism as we discussed to describe the nonlinear interaction. So if you go to modify gravity models, did you compare? So it'd be very useful to compare also to n-body with full modified GR to see whether the formalism is robust. So did you do this comparison?
Yes. So
this fully, beyond GR.
Yeah. So if you look at this, for example, this is the plot which I showed in a hurry, which was by Hassani et al. And Lombrizer. So they have actually modeled. So this is for Yukawa screening, and this is for NDGP screening. They have shown the sort of the expected model from spherical collapse models. And if I haven't shown this here, I can show you this later. It's not in the slides right now because I didn't have that much time. But if you normalize it to the scales that they have normalized, I mentioned that you need to, if you want to compare and if you want to include the changes with D plus, you need to normalize it. Sorry, you need to normalize it with this factor. So once you include this and do the whole Taylor expansion thing, you actually do end up with very similar power spectrum.
And that's the residual. What is this B?
B is just the sort of the this constant. So they're trying to, what they do is that what Hassani et al. Do is that they have spherical collapse simulations for say some NDGP model. And they're like, okay, what if our gravitational constant was parameterized like this? Can I get the parameters like that? So for all these parameters for the models that we use in our KFT calculations, they've gotten from fitting it to the,
It's not a full n-body. This is like a halo model.
This is, I think, spherical collapse model.
Spherical collapse. Okay.
Yeah. So they capture deviations, and then you can see the exact form of A and B. And if using these B equal to 3 parameters, if we do it in KFT as well, we get pretty good agreements. Yeah.
That's what you're doing. Yeah. For different. So of course, you have to look at different possible models. I think it would be good to compare with full simulation.
So if I understood correctly, you do need delta nonlinear to get the trajectories, right?
I do what?
You
Sorry.
do need delta nonlinear to get the trajectories.
No, so we do have a form of so the nonlinear power spectrum depends on the linear power spectrum, which you already know pretty well from.
But how do you get that SL, SI?
It's from the formalism of KFT. I can talk about it more later, but it's an extremely detailed calculation using.
So nowhere you do need the delta nonlinear, right?
No.
You don't need any information from
No, the delta
simulations.
nonlinear is, so once you have the 2-point cumulants of the delta nonlinear, you get this power spectrum. And this power spectrum depends on the linear power spectrum and this interaction.
But okay, fine, I understand. But then what Arka was asking is that this is still the first order or the 0th order term in the expansion, okay? Do you need 0th order term, right?
It's the first order term in the interactions.
Correct.
So the interactions, yes. So it's sort of like a mean field averaged approximation.
So do you need to worry about the next order correction term in this formalism?
We have been working on better ways.
How large or small could it be? As
Right.
to
So you can see from this thing that it doesn't affect too much. Because but once you start to go after a certain wave number, the mean field approximation.
No, why I'm asking this is because in the context of the LSS of the effective field theory of large scale structure, remember when you start adding the higher order terms, the power spectrum goes up or down, and you really need to fine tune the terms that you need to order to make it consistent with, let's say, n-body simulation. Correct.
Yeah.
So will that sort of the same thing happen here, in the sense that if you add next order terms, will it go off and on, and
yes, a little bit.
Okay, thanks.
Okay, if there are no more questions, let's thank all the speakers for this session. And we'll meet back at 2:30. We'll have a talk to start off the afternoon session today, unlike the other days.
Thank you.